Hi, I'm the Wannabe Coder, and welcome back to the Pac-Man and Python series. This is episode 2, and in this video, we're going to start building the maze. Here's what the final result will look like once we're done. We'll begin by talking about how the game grid is structured, why I chose this layout system, and how it helps us place tiles like walls, pellets, and power pellets. Then I'll show you how the maze is defined using simple text, where each character maps to something on the screen. After that, we'll start coding and bring the layout to life using Python's Turtle module. Let's get started. First, let's quickly recap what we did in the last episode. We created a file called main.py with the core structure of our game. It includes 3 main functions: init screen, to set up the game window, game loop, to handle real-time updates, and main, which ties everything together and starts the game. Right now, if we run the code, we just get a blank screen. But that's exactly what we need as a starting point. Now, let's talk about the grid and how it defines the layout of our game. Using a grid makes it easier to organize everything on screen. Walls, pellets, and even ghost paths all follow a clear structure. It also helps with alignment, spacing, and makes the logic behind the game easier to manage. By default, the turtle shape is 20 by 20 pixels. For this project, I chose a slightly larger cell size of 30 by 30 pixels, and there's a reason for that. The size of each cell directly affects the visual scale of the game. Smaller cells let you fit more of the maze on screen, but everything becomes smaller and harder to see. Larger cells make the objects easier to see, but they limit how much you can fit within the screen space. With 30 pixels, I found a good middle ground. It's big enough to keep things readable, but small enough to fit a full maze without crowding the edges. This cell size also helps us plan how large to draw each tile, like walls, pellets, and power pellets. To make everything look clean and well aligned, we'll draw those shapes slightly smaller than the cell, just enough to leave room for padding and spacing inside each tile. So in short, the grid gives structure to the entire game, and the cell size you choose has a big impact on how your game looks, plays, and feels. Now, let's take a look at how the turtle graphics screen works, and how we set up its dimensions to match our grid layout. In our game, we're currently using a screen that's 1000 pixels wide and 800 pixels tall. These are the inner dimensions, meaning the actual drawable area, not including window borders. In Turtle, the coordinate system is centered. That means the point x equals 0. Y equals 0 is located right in the middle of the screen. So the top right corner is at plus 500, plus 400, and the bottom left corner is at minus 500, minus 400. This is important to understand, because it helps us calculate where things should go on the screen, and ensures that everything we draw fits exactly where it should. Now, the screen size we used earlier was chosen a bit randomly, but now that we've locked in a cell size of 30 pixels, we'll want to update our screen width and height so they divide perfectly into full grid cells, with no leftover pixels at the edges. Before we do that though, we need to think about how we're using the screen. Besides the maze itself, we'll also want to display extra game info, like score, lives, or messages to the player. So in this layout, I'm going to reserve the top 2 rows of the grid for that kind of data. That gives us space for UI elements, without interfering with the gameplay area below. Alright, now that we've covered the layout and planning, let's go back to our code and update the screen dimensions we set up in episode 1. First, let's decide where we'll keep our grid settings. Now technically, we could define everything, like the cell size and screen dimensions, right inside our main.py file. But it's a good habit to keep your constant values in a separate file. It helps keep your code organized and easy to read, especially as the project grows and more pieces get added. It also means that if you ever want to tweak something like the screen size or grid layout, you'll know exactly where to look, and you won't have to scroll through your main game logic to find it. So with that in mind, let's create a new file called constants.py. Make sure it's in the same folder as main.py. Then go ahead and open it in your code editor. because we're about to define the key settings for our grid. Let's walk through the constants.py file. This is where we store all the fixed values that define the grid and screen layout for our game. At the top, there's a short comment explaining the purpose of the file. It says this file contains all constant global variables. Constants are variables that don't change while the program runs. By convention, we write them using uppercase letters, so they're easy to recognize. Now let's look at the actual values we've defined. We start with the cell size. Cell_size equals 30. Each tile in the game, like walls or pellets, will be drawn inside a 30 by 30 pixel square. This value becomes the foundation for all of our grid calculations. Next, we define the screen dimensions. Screen_width equals 1000. Screen_height equals 850. We set the screen width to 1000 pixels and the height to 850 pixels. Now, to be honest, I picked these numbers a bit arbitrarily, but I chose them with one thing in mind. I wanted the screen to be evenly divisible by our cell size of 30, while leaving a small margin on each side. For example, 1000 divided by 30 gives us 33 columns with 10 pixels left over, and 850 divided by 30 gives us 28 rows, again with 10 pixels left over. That extra 10 pixels is perfect for centering the grid by giving us 5 pixels of margin on each side. This sets the total size of our game window. We'll use these values when setting up the turtle screen, so everything lines up properly. Now we calculate how many rows and columns fit on the screen. Grid_rows equals screen height / cell size. Grid_columns equals screen width / cell size. Here, we're using integer division to see how many full 30 pixel cells fit vertically and horizontally. This gives us the size of our full grid based on the screen dimensions and the cell size. Then we calculate the margin on each side. Row_margin equals screen width minus cell size times grid columns, all divided by 2. Column_margin equals screen height minus cell size times grid rows, all divided by 2. Sometimes the screen width or height isn't a perfect multiple of the cell size. These calculations make sure the grid stays centered by dividing any leftover space equally on both sides. There's a note explaining that the full screen grid is 28 rows by 33 columns, and that leaves a small margin of 5 pixels on each side. That's what the two margin values are for. Next, we define the maze area inside the grid. Maze_grid_rows equals grid rows minus 2. Maze_grid_columns equals grid columns. We subtract 2 rows from the total grid height because we're saving the top 2 rows for things like score, lives, or messages. So the maze itself only takes up the remaining rows. Finally, we calculate the starting x and y coordinates for drawing the maze. Maze_level_ start_x equals negative screen width divided by 2 plus row margin plus cell size divided by 2. Maze_level_ start_y equals screen height divided by 2 minus column margin minus cell size times 5 divided by 2. We start drawing the maze from the top left corner of the playable area. For the X position, we move in from the left edge of the screen, then add the margin and go half a cell further to land right in the center of the first column. For the Y position, we move in from the top edge of the screen, then subtract the margin, then go down 2 full rows to skip space for score and lives, and go half a cell further to center the first tile in the third row. This tells us where the top left corner of the maze should be, based on the center of the screen, the margins, and the size of one cell. The math might look tricky at first, but all it's doing is figuring out where to place the first tile of the maze, so that everything is positioned correctly on screen. So, in summary, this file contains everything we need to calculate and align the game layout. And by keeping it all in one place, it makes the rest of the code simpler and easier to manage. Now that we've set up the constants, it's time to define the maze itself. We'll do that in a new file called mazes.py. This file should go in the same folder as main.py and constants.py, so everything stays organized and connected. Go ahead and create a new file called mazes.py and open it in your code editor, because we're about to define our first maze and write the code that turns it into something the game can actually use. Let's take a look at the mazes.py file. This file contains two things: the maze layout itself and a function that reads that layout and returns the positions of all the walls, pellets, and power pellets. At the very top, there's a short comment explaining the file's purpose. It tells us that this file stores different maze levels and includes the logic to convert those levels into usable coordinates for the game. It also explains how the layout works. Uppercase X means a wall, a dot means a regular pellet, and uppercase O means a power pellet. Next, we import a few constants from the constants.py file. We import the cell size, the number of rows and columns in the playable grid, and the starting X and Y coordinates for drawing the maze. These values are essential for calculating where each tile should be placed on screen. After that, we define the maze itself. We create a variable called maze_level_1 and assign it a list of strings. Each string represents one row of the maze. Each character inside the string represents a tile. X is a wall, dot is a pellet, and O is a power pellet. This layout must match the maze area grid dimensions we defined earlier, specifically 26 rows by 33 columns, because we reserved the top two rows of the screen for UI elements. Now, let's look at the function that turns this layout into coordinates. The function is called calculate_maze_data. It takes one input, a maze level, like the one we just defined. Inside the function, we create three empty lists: walls, pellets, and power_pellets. These lists will store the X and Y coordinates of each item in the maze. We start by looping through each row in the maze from row 0 up to the total number of maze rows. We use the range function for this. It gives us all the round numbers, starting at 0 and stopping right before the maximum. Inside that loop, we loop again, this time over each column in the current row. Again, we use the range function, this time with the total number of columns. This two-level loop is how we scan the entire maze layout. The outer loop goes row by row from top to bottom, and the inner loop goes column by column from left to right. So by combining them, we can visit every single character in the maze grid and figure out what's there and where it should go on screen. To get the character at each position, we use the row and column indexes together. In code, that's written like this: character equals maze_level, open bracket, row, close bracket, then open bracket, column, close bracket. This gives us the tile symbol at that location, like X, dot, or O, so we know what belongs in that tile. For example, if the row is 5 and the column is 10, we're reading the 6th row of the maze layout and the 11th character in that row. That tells us exactly which tile we're looking at and what it represents. Then we calculate the X and Y position on screen for that tile. The X position is calculated by starting at the maze's starting X coordinate and adding the cell size times the column index. The Y position is calculated by starting at the maze's starting Y coordinate and subtracting the cell size times the row index. This gives us the exact pixel location where the tile should appear on screen. Remember, since row and column counting starts from 0, the first tile is placed at the start position with 0 offset, and each step forward increases the offset by 1 cell size. So row 1 is 1 cell below the start, and column 1 is 1 cell to the right. Now comes the logic. If the character is X, we add its coordinates to the walls list by typing walls.append and passing in the X and Y position. If it's a dot, we add the position to the pellets list. If it's an O, we add it to the power pellets list. After scanning the entire layout, we return all three lists: walls, pellets, and power pellets. This makes it easy to use the data in other parts of the program, like drawing the maze or checking for collisions. So in summary, this function converts a visual layout made from simple text into real, usable coordinates for our game. And because it returns the data as separate lists, we can access and use that information anytime we need to. So to recap, in the mazes.py file, we defined our first maze layout using simple rows of text, and we wrote a function that reads that layout and calculates the position of every tile on the grid. The function goes through the entire maze and figures out exactly where the walls, pellets, and power pellets are, based on their position in the layout. It stores all of that data in three separate lists: one for walls, one for pellets, and one for power pellets, so we can later use those lists to draw the maze on screen. This keeps the layout logic separate from the main game code and makes it easy to update or add new maze levels as we go. Alright, before we wrap up, let's take a moment to look back at what we've built in this episode. We started by learning how to define a grid, and we chose a layout that works well for our Pac-Man game. We created a file called constants.py, which stores all the important values that control our grid, like the cell size, screen dimensions, margins, and starting positions. Then we created a file called mazes.py, where we defined our first maze level using simple text, and wrote a function that turns that text into actual screen coordinates. That function loops through every tile in the maze, and stores each wall, pellet, and power pellet in its own list, so we can use those positions later when we draw the maze on screen. Back at the beginning of this episode, I mentioned that we'd have a fully drawn maze by the end, but since we've already covered quite a bit, I think it makes more sense to pause here and take our time with the next step. In the next episode, we'll focus entirely on drawing the maze, one piece at a time, using the coordinates we've just set up. If you found this helpful, a like and subscribe would really help support the channel, and make sure you don't miss what's coming next. I'm the Wannabe Coder. Thanks for watching, and I'll see you in the next episode.